Great. So it's a couple of minutes past noon. Let's get rolling. Looks like we've got quite a few attendees joining at this point. This is Steve McInerney at TerraTherm. We'll be doing our presentation today, and the topic, as you're aware, is vapor treatment optimization approaches and safe and effective compliance strategies. In terms of an overview, a bit of background about myself. I've got 27 years of remediation and industrial air and water treatment, 3 of which have been at TerraTherm. I'm currently the engineering manager and the process engineering discipline lead for TerraTherm. And back in my early days out of college, I'd helped develop and commercialize a high-temperature thermal desorption process at a company called Retec, again back in the 1990s, and that was focused on contaminated soils and refinery wastes and the like. In terms of a little bit of orientation, kind of frame up what I'll be covering for today's topic. I'll be talking about a range of vapor characteristics that come from our well fields for various thermal projects, both looking at low temperature thermal desorption and higher temperature thermal desorption approaches. The focus of the presentation, I'll be looking at the use of activated carbon systems and thermal oxidizers with a real focus on a vapor, what I call preconditioning, to make sure that the vapors entering the carbon systems and oxidizers are properly conditioned to maximize the benefit and the cost effectiveness of the carbon and oxidizer systems. I'll also be talking about briefly some other related unit operations that kind of focus or complement carbon and oxidizer systems. We will get through the presentation hopefully in about 30 to 35 minutes, maybe a little bit longer. And if folks can, as they go, add questions through the website here. We'll have a brief question and answer session based on the timing. We want to keep this well within an hour. I'll try to hit most, if not all, of the questions that we have here, and if necessary, follow up. And by all means, we really do want the feedback from this presentation. And if everybody here in attendance could take care of the accessing the survey at the end of the webinar, that would be much appreciated. This is just a repeat here again to add your questions, if you could, to the question panel. And again, as discussed, we'll hit that towards the end of the program. So just a high-level overview, pointing out here that TerraTherm does represent and deploy all 3 of the major thermal remediation techniques available in the marketplace. Many of our projects deploy thermal conductive heating. We also look to do electrical resistance heating and steam-enhanced extraction. And the point of this slide really is to show that the ISTD or thermal conductive heating approach gets into potentially 2 different ranges of treatment. One we'll call low temperature, up to the point of a boiling of water at or about 212 degrees Fahrenheit. And then also when you fully dewater a site and get into higher temperature operations, the TCH approach that applies and gets to much higher temperatures than 200 degrees Fahrenheit. Whereas the ERH and C remediation techniques are really limited to the boiling point of water, and we're talking about lower temperature vapors that would emanate from those treatment technologies. So in terms of vapor characteristics, sort of our starting point here, at a high level, thermal sites are typically highly impacted. We've got high mass in the source areas, and the projects are really focused on short duration, trying to get in and out and remove as much mass as we can to meet the objectives of the project. And that translates to, at times, very high loadings to our vapor collection and treatment systems, and very dynamic conditions where we may start out at a cold site with very low loadings in terms of flows, condensable, non-condensable, and contaminant impacts that will ramp up as we approach or reach the boiling point of water. And after much of the mass has been depleted, then the contaminant concentrations would then tend to trail off. So things are constantly changing, and sometimes changing fast at a thermal site. In terms of the extracted vapors and what they look like, when we're talking about low temperature thermal desorption, when we get up to that boiling point of water, we're approaching the point where the vapors we're collecting from the well field, combination of air and produced vapors and water vapor, can be upwards of around 200 degrees Fahrenheit based on that air to steam mix. And they're essentially saturated at about 100% relative humidity. And again, it's carrying with it oftentimes a VOC loading and some steam-stripped SVOCs, depending if those are there and how long we've been remediating the site at that low temperature range. When you get into the high temperature operations, we're talking about vapors ranging from 250 degrees Fahrenheit to sometimes about 400 degrees Fahrenheit, and we're talking about drier gases, very low humidity ranges, and again, for the higher temperature operations, we're sort of focused on the higher boilers, removing the SVOCs, could be PAHs. We're talking PCB type sites and maybe dioxin sites where we're focusing the high temperature thermal desorption. And again, in terms of a characteristic that we routinely run into at chlorinated and fluorinated sites, this often acid gas is produced as a byproduct of in situ destruction of these COCs. So another sort of operational concern that we're focused on in the presentation here. And just pointing out in the last bullet here that these sites, once we start heating and get at or above the boiling point of water, there's a lot of residual heat that when we have a power failure or any sort of equipment shutdown scenarios, that water vapor, contaminant vapor, and whatnot still is continuing to be generated in the subsurface, and we need a strategy to make sure that we continue to capture those vapors during those operational scenarios. So again, looking at the range of operating conditions, when we're talking about the warm and humid portion of the program here, again, saturated up to 100% relative humidity and higher temperatures. The amount of moisture really creates a significant opportunity here to look at cooling and condensing that condensable portion of the vapor stream, and thereby shrinking the footprint and the capital costs of the vapor treatment equipment that would be downstream of the conditioning step. And that again leads to both capital and operating savings. When you get into the hot and dry period, again, recognizing that typically you've got to go through a warm, humid, low temperature phase to boil off any of the water in the treatment zone before you get to a high temperature. So you've got to go through those two phases typically. The hot vapor scenario kind of creates an opportunity where, if you're not after cooling this material but leaving the vapor hot entering the oxidizer, you've got the ability to kind of control the amount of fuel that you would need to add to the oxidizer, supplemental fuel, to get up to the desired temperature in the oxidizer. When you do that approach, oftentimes you're looking at some unique equipment configurations where the high temperature vapors, upwards of about 400 degrees Fahrenheit, really aren't suitable to be passing through a blower that would then push the vapors through the oxidizer. Oftentimes you're talking about an induced draft configuration with the blower after the oxidizer scrubber. And there are other special design considerations around that kind of configuration where the entire system is under negative pressure or vacuum. But when you're not looking at an oxidizer, most definitely you need to be looking at cooling before you get into an activated carbon system. When the project requires something less than an oxidizer, really need to cool that gas to get down to the sweet spot of the absorptive capacity of the carbon. We'll talk a bit more later in terms of high boiling condensable contaminants and strategies for taking that out of the vapor and getting into a liquid. We'll talk a bit more about acid gases and then high LEL vapor streams and how to manage those safely. So pointing out in this slide that really much of the focus again is on how we pre-treat or manage and condition the vapor streams going into a carbon system or a thermal oxidizer. these are really the bread and butter technologies that the TerraTherm deploys. But we certainly get into some of the other items in terms of secondary vapor control strategies like synthetic media, steam regenerated activated carbon condensing systems, and then other impregnated reactive media. But again, the focus is on the top two. So vapor phase carbon, I think most of the folks in the audience are extremely familiar with this. I'm not going to get into a lot of detail, but as we all know, they're very simple, simple flow-through type systems that are easy to install and operate. Broad industry regulatory acceptance of this as a control technology, and generally speaking, some pretty predictable mass loadings. Range of contaminants may average about 10 to 15% by mass contaminant absorbed to the carbon media. And of course, that can be much higher for certain contaminants and much lower for items like, say, vinyl chloride or much lighter or lower molecular weight, high volatile compounds can tend to be significantly lower than that 10 to 15 range, but that's sort of a rule of thumb. I'm not going to get into all of the design details around it, but just sort of recognizing that certain contaminants have got a heat of absorption that could cause some problems with carbon in terms of the risk of bed fire and other operating conditions like that. So they're not foolproof systems, and anytime you've got the right mix of contaminants and the right operating conditions, you need to make sure that the systems have got built into it some safeguards to detect temperature rise in the beds and be able to isolate these systems and prevent a breakout of a bed fire. But of course, carbon, unless you're talking about an on-site regen type approach, we spend the media on the site, and it requires recycling or off-site disposal. And carbon can tend to be the cost-effective approach for lower mass sites, but sometimes, based on the amount of material at a site, it just makes sense to bring out the big guns and go with the thermal oxidizer. So at a high level, when you're talking about performance of an activated carbon system, really three kind of key pieces of the puzzle that would affect the absorptive capacity. Beyond the contaminant type, we're talking about concentration, where you've got higher concentrated vapors. You tend to have better loading on the carbon pound per pound. The opposite is true for temperature. At higher temperatures, you get lower absorptive performance, generally speaking. And with humidity, the higher the humidity, the lower you would expect to get in terms of absorptive capacity. In the lower curve, you can see that the humidity absorption curve here, at or about 50% relative humidity, the absorption of water into a carbon bed really accelerates. And so kind of an industry rule of thumb is you want to be at or below 50% relative humidity. So when you're conditioning your gas stream and designing a system to do that, that's really your target. And again, if you can look at the isotherm curves here, you can see that at the higher temperatures you get much lower absorptive capacity, and that improves as you reduce the temperature. And we focus on TerraTherm being at or below 120 degrees Fahrenheit as often as we can to really beef up the absorptive capacity of the carbon and reduce the amount of waste that we have to deal with off-site. Briefly, this is a curve sort of showing that the amount of water in a vapor stream is not only a function of the temperature, but also the pressure of the gas stream, where our operating conditions may range anywhere from, say, at the well field to the suction setup or blowers at say 30 inches of water column vacuum, up to a practical limit of, say, a positive 30 inches of water column pressure. And you can see, looking at this chart, that the range of I guess moisture carrying capability of those vapor streams under various pressures do change, and it's something that we keep track of, and we've got functions built into our Excel mass and energy balance models that kind of look at that carefully throughout our treatment process. So looking at a typical process flow diagram here, to the left here, we've got our well field vapors getting into a cooling and condensing step through a heat exchanger, knocking out the condensed moisture, and this is really where you get, upwards of say 50% volume reduction for all of your downstream treatment equipment. Many of our systems are configured to induce draft through the well field and then push or force draft the vapors through activated carbon, but we do have examples of where the blower is set up after the carbon to do induced draft all the way through the system. Talk a little bit here about choosing the right cooling approach, whether it's cooling tower versus chiller. I've got some slides that will follow on that. And the point of highlighting here the duct heater is that don't always need them. Based on the heat of compression through the blower, we would expect to see a temperature rise. And based on the temperature pressure curves that I showed you earlier in the slide, if we can avoid the extra energy added through this duct heater and get at or below or pretty close to the 50% relative humidity that we had talked about, then as often as we can get away with not running a duct heater, we would elect to do that. And pointing out here that the choice of using a chiller versus a cooling tower is really sort of an economic one, where there's benefits to both cooling type approaches. There are other commercially available types, but that's really, again, the bread and butter of TerraTherm's systems are either chiller or cooling tower. And sometimes those decisions are made on other factors like, well, what heat exchangers do we have available, and can we get enough cooling for this particular project based on an existing piece of equipment with a cooling tower, or do you need to invest in a chiller? So I'm not going to get into the cooling tower design considerations in a lot of detail here, but really, we're talking about a weather-dependent system. Where you situate this equipment will dictate how, the quality and the temperature of your cooling water. Hot and humid locations are much worse than cool, dry locations in terms of just how much heat exchange you could expect through these devices. They tend to be loud, noisy equipment, and because you're at the mercy of Mother Nature and potentially have got higher temperatures of the cooling water loop, based on a cooling demand that often translates to needing larger heat exchangers to get the amount of cooling you need for the project. The benefit of these is that, again, you're dealing with evaporative cooling and ambient temperatures to provide the cooling effect we're looking for. And so they can be low utility cost type cooling applications. They're simple to operate, high octane, not a lot of complicated controls to shut the systems down. But the real trick with cooling towers, beyond just situating it and understanding the weather and how well you'll get the cooling that you're looking for, you need to manage water quality. Look at the quality of the water coming in, the fact that we're evaporating water to get the bulk of the cooling. Anything coming in terms of contaminant, total dissolved solids, particulate, that sort of thing, will tend to get concentrated over time. And you really need to be careful about setting the right blowdown and looking at issues like biological growth. These can be large bioreactors at times, and possibly needing to add biocide and other additives to make sure that the water quality is there and doesn't impact your process systems. On the flip side, coolers, you pretty much can dial in the operating temperature you're looking for, down to or even below the freezing point of water with a glycol mix. And so with the cooler temperatures that you can expect from a chiller, you can use much smaller heat exchangers because of the larger driving force between the process and the coolant fluid. The packages themselves can tend to be smaller and quieter than a cooling tower. And we get a lot of sites where a cooling tower may be the right process election based on where the site is situated, but sometimes there are neighbor concerns in terms of just large, visible, noisy equipment that really sort of dictate the need to go with the chiller as opposed to strictly process conditions making that decision for you. But they're higher utility costs. It's basically a large refrigerator, and you're paying a premium for electricity to get the cooling. compared to a cooling tower. And one of the benefits, I guess, is to look at the water or glycol mix or whatever you use for the cooling fluid. It is a closed loop. There is no evaporation component to it. So a lot less sort of management considerations in terms of water quality and residuals you need to watch for. And the real drawback, I think, with this equipment is that it's complicated. There are a lot of control inputs and outputs to the control center for these units. They're prone to shut down, and if high uptime is important, then chiller may not be the best choice. Briefly, I'm not going to look at the liquid side of this slide, but on the vapor side, we've got a fleet of shell and tube type heat exchangers that we typically use for cooling condensing operations. Often go duplex or even triplex, where we've got one heat exchanger that's online at any one time and a fully redundant spare in the event that one unit needs to be taken offline for service. We'd like to double up on our equipment. Often use graphite type heat exchangers for corrosion resistance for any sites that would be potentially generating the hydrochloric, hydrofluoric acids that I talked about earlier. We go with the graphite style, whereas if non-corrosive issues or hydrocarbon type sites are what we're dealing with, then carbon steel or stainless steel type exchangers would be appropriate. And just sort of pointing out that the graphite units, as much as they're terrific in terms of corrosion resistance, they really do have an upper operational limit on the vapor side of about 350 degrees Fahrenheit, which may not be sufficient for a lot of our high temperature operations, whereas the metallic type can go to much higher temperatures. Just quickly stepping to lessons learned here, one thing that we've added to a lot of our O&M data management is to track U values. And those that have taken heat exchange back in the day, U value really is sort of an indicator of the ability of an exchanger to transfer heat. And when U values deteriorate, that's an indication that the exchangers themselves may be fouling, or there's a change in process flow conditions through the unit. And when those U values deteriorate, it's time to think about service or a closed system inspection. Again, talking about graphite, it's extremely expensive, it's fragile, and there's extra care that needs to be put into handling, shipping, and servicing these equipment, because it's quite an expensive ordeal to replace or repair these. This image is sort of looking at kind of a unique set of circumstances for a project that we're currently deploying. This is a high temperature operation going after dioxin, and the dioxin site actually had the potential for condensing NAPL of other organic materials, the potential to generate acid gases, and a whole host of different operating conditions that needed to be factored into the vapor control strategy here. So because we had the corrosion issues that I talked about earlier, this particular heat exchanger setup was a graphite unit, and we had much higher temperatures than 350 degrees Fahrenheit. So we really did need an initial cooling step that we used a quench/scrubber system to knock down the temperatures from the high temperature dry vapors coming from the well field. Again, adding water, getting the evaporative cooling through that step, and then the resulting vapors exiting the scrubber would be at or slightly above 200 degrees Fahrenheit or so. A temperature that we could easily handle the bulk of the remaining cooling load and condensing step through a shell and tube heat exchanger. Because we had condensing NAPL, the typical setup for recirculating scrubber bottoms right back to the top of the tower in a loop like this really wouldn't work. The concern is there that it might emulsify some of the condensed organic material and really make a mess inside this operation. So the bottoms really went for a much longer ride in a recirc loop here, where we pump the bottoms through a filter, cool it through another heat exchanger, into an oil water separator to separate out the NAPL, and then the clarified water would then get recirculated back to the scrubber again in a much broader loop. And because of the potential to have acids condensing in the system, we had a neutralization step with sodium hydroxide in the recirc loop on a pH control setup. This particular site used a blower at the very tail end. So in terms of the draft configuration, everything from the well field all the way through the vapor control step of carbon was under induced draft. And because we are essentially at dew point coming out of the heat exchanger and vapor-liquid separator, we absolutely needed to reheat this vapor to get the relative humidity adjustment down to 50% that we had talked about earlier, and try to optimize the carbon performance. So again, looking at a sort of a complicated, multifaceted control approach for trying to manage the vapor conditions and try to optimize that for our best absorptive capacity in the carbon. So shifting over now to oxidizers, really there's pretty robust equipment, better suited for higher loadings for sure. In terms of the contaminant mass at a site, you get a lot of flexibility to really sort of select the equipment and dial in the destruction and removal efficiencies you're looking for. And the key parameters there are what is the residence time in the oxidation chamber, and what is the operating temperature at that residence time. When you need higher DREs, you go for longer residence time and higher operating temperatures. Very capital and operating cost intensive type systems. The benefit is that everything is essentially destroyed or neutralized through the process, and unlike carbon, you don't have the waste material. Again, as mentioned, well suited for high mass sites. We absolutely look at designing in reliability and flexibility into the systems, making sure that we got plenty of redundancy, spare equipment, spare parts stored at a site. And with this much more complicated, sophisticated equipment, we really do need to rely on very experienced and well-trained operators that can both handle the equipment and kind of recognize the dynamic and changing vapor conditions at these sites and respond appropriately. This next slide is just a picture of an oxidizer, and this is not a typical oxidizer. This happens to be one that was designed for high temperature PCB destruction, and the basic components of this oxidizer are similar to others, but there's some unique elements to this that I'll point out here quickly. This site, if you're following the cursor, we used a heated inlet line, so the strategy was not to cool and condense for the higher temperature phase of this project, but we wanted the highest temperature we could maintain going into the oxidizer, so that we didn't need to make up more supplemental fuel to get up to the operating temperature of this unit, which was approximately 2,300 degrees Fahrenheit with a 2-second residence time. Many oxidizers coupled with a heat exchanger would preheat the well field vapor inlet. This unit is a little bit unique in that we're preheating the combustion air supply, basically ambient air pushed in through a combustion air blower, as opposed to trying to preheat the stream that's already hot. That created some issues in terms of the design of the heat exchanger here. And a couple more things to point out. The heat exchanger here, the materials of construction were such that the operating limit of that unit was approximately 1,800 or 1,900 degrees Fahrenheit. The vapors exiting the chamber here were closer to 2,300 degrees Fahrenheit. So some of these breather vents that you see that I'm pointing at are there so that under induced draft we could breathe in some ambient air and thermally dilute that exhaust temperature and get it down to or below the operational limits of the heat exchanger here, so we wouldn't overheat and damage that unit. Then off to the right here in the background, you see the quench system. That's the first place that we knock down the temperature significantly with evaporative cooling of water. And that's a metallic structure. That's a Hastelloy tower, followed by an FRP scrubber system. And as you could well imagine, you really don't want these, 1,000+ degree Fahrenheit vapors entering a big plastic vessel like this. It's ultra important that we get good water quality and an adequate supply of water in the quench system and knock down the temperature before the vapors flow into the scrubber, or we can get ourselves into trouble. So, quick time check here. We're at about a half hour. I got about 5 or 6 more minutes to go here. Looking at some strategies here for managing high mass sites. This is a typical curve that you might expect to see at a thermal site, where you can see early on in the project, before things heat up, not a lot of vapor mass is being emanated and collected in our systems. At some point, you reach a peak when you get up to, say, the boiling point of water or so, or at least the boiling point of the contaminants. And then at some point, after the mass is depleted again, the amount of mass or the concentrations heading towards our vapor collection and treatment system tend to drop off. So just pointing out here that at the beginning and the end stages, these phases of the operation need to be considered. The real key is looking at the peak and what that translates to in terms of impacts and sizing requirements and how you'd operate your vapor treatment equipment like a thermal oxidizer. So this is just a brief project example, a project we recently completed down in Connecticut, where we developed a phased approach so that we could really control the amount of material and the concentration of the material impacting thermal oxidizer for this project. The concern was that if we went after this entire site, which was predicted to have anywhere between, say, 500,000 and 2 million pounds of DNAPL in it, that if we hit this all at once with our heating strategy, that would overwhelm an oxidizer of a certain size or require a much larger oxidizer with potentially a lot of dilution air to make it operate safely. So we tried a phased approach where we would heat phase 1, get through the peak organic generation phase. After we get off the peak of phase 1, we would then initiate heating and ramp up heating of phase 2. And I'll show you what that kind of looks like in a curve here, where the left side of the curve here kind of represents what we're expecting for phase 1. The next curve here in yellow represents what we were expecting in phase 2. And then the combination of the two is represented here in the red line. And again, this is exactly what we deployed. The actual curves are a bit more discontinuous than this, but this is the idea here, and it worked very, very well in terms of limiting the size of the oxidizer that we needed to specify for this particular project, and really helped us control the amount of fuel that we would need during those earlier and later phases of the project, and ended up being a great operational strategy for us. One thing to consider when you're talking about approaching the operational limits of an oxidizer, you need to be careful about the LEL level, where any thermal oxidizer that's governed under NFPA 86, NFPA 86 will tell you that you can operate an oxidizer up to about 50% of the LEL, provided that you've got continuous LEL monitoring. Anytime you expect to exceed 25% of the LEL. NFPA 86 also requires that the LEL sensor and reading is adjusted or corrected for temperature. And whenever you've got a heat exchanger like this, you can see in this diagram, the LEL sensor is on a cooler portion of the vapor ducting. These devices often can't handle the higher temperature of the preheat, so practicality reasons, the sensor needs to be located in a cool location, but then auto-corrected for the preheated temperature to make sure that we don't read, closer to ambient reference LEL and actually have a much higher and unsafe condition because of the preheat, and you need to make sure that you're monitoring and alarming to that correction for temperature. Moving on here, this is an example of a project that we completed at the pilot scale, and what's shown here is sort of a strategy for full scale, but some of the elements that we tested in the pilot are worth mentioning here. Here's a technique here that we used for a site where we expected from our well field VOCs at a concentration that would exceed 100% of the LEL, and some of the contaminants had relatively low auto-ignition temperatures. And based on the way that this pilot cell was configured, there was a headspace above the waste material where our heater was exposed up into that headspace. So the concern is that any vapors that would be at or above 100% LEL and with low auto-ignition temperature in contact with our heater would be a problem. So the strategy for operating this site safely was to nitrogen blanket over the waste material and inert to or displace the oxygen so that we remained below 5% O2, which was well below the level that would sustain combustion. In this particular site, we maintained consistently through the pilot program O2 levels closer to the range of about 1 to 1.5% O2, maybe 2% at the most. So we're well on the safe side of the operation there. You can see that we're monitoring O2 and alarming based on those levels. We did use an oxidizer at the pilot scale and plan to do so at the full scale to make sure that we stayed slightly below saturation. We did have a duct heater here to make sure that any mist or water wouldn't be impacting the oxidizer as it flowed in. And just before we went through the blower system for the oxidizer, we had oxygen and LEL sensors, and we controlled the amount of air being diluted in on the suction side of the blower so that we could get down below 50% LEL and have sufficient oxygen to sustain combustion through the oxidizer system, and then and through the scrubber and on out to the stack. So again, kind of a unique approach. We don't often do this, but this is something that I used to deploy quite a bit in my early days at RETEC, where we had continuous conveying thermal technology with absolutely a vapor space and concerns about contact with heating systems. The way to manage that was an inert system that looked just like this. This slide really kind of recognizing that there's another beast out there entirely when you're talking about thermal oxidation. TerraTherm currently owns 2 thermal accelerators. Essentially, it's a flare-in-the-box style design without a heat exchanger, and really well suited for high BTO content vapors. And these particular units are not governed by NFPA 86 in that they can operate at above 100% LEL. The units that we own can run on multiple fuel platforms, natural gas, they can run on propane, and they're currently deployed at a site where we're recovering jet fuel. And we're using that jet fuel that we recover at the site, conditioning that, and using that now as a supplemental fuel to fire these oxidizers. Capacity, again, the 2 units are about 2,500 CFM each. And the way that these things are operated safely is that there's a very narrow throat leading into the oxidizer, and we maintain very high inlet vapor velocities feeding the unit, so there's no risk of backflash. And we absolutely couple that with flame arresters and other instrumentation to make sure that it's operating in the safe operations range. I think we're closing in on the end of the slides here. Just wanted to sort of recognize a technique that we routinely use at sites where HCl or HF generation is a byproduct of thermal decomp, and that can really cause problems with our materials of construction for vapor liquid treatment systems if we don't manage that acid. And the issue is that those generated acids may be coming out in a vapor into our header. Our well field vapors, as I pointed out earlier, are often at 100% saturation. We start to condense water in our vapor piping. And so a little bit of water and a bit of acid The acids are very hygroscopic. They're loving water, and that translates to potentially very low pH water entering the head of our equipment. And again, that's quite damaging to metallic treatment components. So we often dose a caustic solution in through a spray nozzle into the well field vapor header as it flows into a vapor liquid separator, or similarly, we would just recirculate some caustic in the bottoms of this vapor liquid separator and make sure that we're neutralizing at the very front end of our system and not impacting our equipment downstream. This slide just sort of recognizing that one of the earlier points that I brought up at the beginning of the presentation, that some degree of redundancy or strategy for when there is an eventual power outage or equipment failure, say with the thermal oxidizer that needs some time to remedy. We quite often back up our systems with a redundant carbon system when an oxidizer is deployed. And we would have a separate, smaller blower that can operate on a generator at much reduced power. And in that manner, we can continue to draw off vapors from the well field, maintain pneumatic control, and not have the risk of any vapor exceedances out in the well field. We have deployed these carbon systems not only as backup, but also as the primary treatment step. Periods where the oxidizer isn't quite at a place where it's going to be cost-effective to operate. Until you get to that peak, there's an earlier phase of the project and a later phase after the cool down has commenced, where carbon may be the better, more cost-effective control approach for a project, as opposed to firing up the big oxidizer for those periods of low loading. So, kind of a combination of a backup and a primary for those low loading periods. So we're reaching the end of the presentation. Just want a couple of wrap-up points here. Sort of pointing out again that vapor treatment applications for thermal sites can be very dynamic type situations. We've got warm, wet vapors at times. We've got very hot vapors that are bone dry, and a combination of the two when we've got high temperature targets for thermal desorption. Highly impacted sites that we're at, which translates to highly contaminated or concentrated vapor streams impacting our vapor operations. And those changes in terms of concentrations and loadings can happen very, very fast. And as I discussed, there's potential corrosive conditions that need to be managed. So in terms of managing that full range of operating conditions, we really need to have a flexible and robust design that includes spare blowers, pumps, backup supplies to keep our equipment well maintained and operating, and not have to worry about any long lead items for replacements. And as I pointed out, many of our systems require an emergency backup power supply, and with scrubber quench systems absolutely require a redundant and effective water supply system. If we lose the water supply to our quench systems and a hard shutdown for our equipment, that could spell trouble for our FRP scrubber systems. So number one, in terms of reducing the footprint of the capital equipment and the operating costs and all, if there's moisture there and there's an opportunity to cool and condense and shrink the volume, absolutely, that's part of the strategy. Need to carefully maintain the LEL conditions and again manage the acidic vapors. And particularly when we're talking about a thermal oxidizer, the level of sophistication required of that equipment absolutely requires highly skilled and trained operators, and TerraTherm has got some of the best on our staff. So that is it for the presentation. I'm going to look to see what we have for questions. Appreciate you folks hanging in there. Looks like we've gone about 45 minutes or so.